Welcome everyone to Distilling AI. Today's topic is going to be model selection. My name is Amir. I'm a PhD student at KTH. This event has been co-hosted by Marta. She's been helpful, done a lot. So I'm very thankful to have her as a co-host of the event. A little bit about the initiative. Distilling AI, this is my understanding of the initiative. I did not create this initiative. It's about making different ML concepts understandable. The initiative started by Carl. He's in this meeting, and I joined the initiative after talking in Starbucks Cafe in Stureplan. It was the former fortress of Stockholm AI that is now closed. And then after that, we had Ingrid who joined the initiative. We've had 4 sessions based on my knowledge. We covered regularization, we covered interpretability, and we covered ensemble learning. It's been really great. We have been hibernating a bit on the initiative, but now we're taking a continuation of that. So I want to kind of emphasize on the fact that this is about understanding. So taking a complicated idea and make it as much as we can understandable so it sticks. So I think it's a very important initiative because a lot of these concepts, they're very complicated when you look at it. And if you just struggle with it, after a while, they start to make sense. So today I'm going to talk. I owe everyone an apology. I was supposed to send a reference so that you can read about it. However, I've covered a lot of things in my presentation. Formerly, we did not have a very thorough presentation because we assumed that everybody has read about the topic or the subject. After my talk, we're going to be into groups, I think maybe 2 or 3 groups. And whatever the topic is, whatever we understand from the presentation, if something was interesting in the presentation or what we know about the topic, and discuss and trying to really make it understandable as much as we can. And after that, we come back and we basically discuss what we found across different groups. First, I think it's good that the discussions are group-based, so there are few people talking about it, and then once it's solidified or some things can be noise, then when we talk about talk in the main groups in the whole inner group discussion, we can only pick up the interesting parts. Today's agenda is basically has a lot to do with cross-validation. We'll cover also bias variance in cross-validation and even more cross-validation. Originally, I wanted to cover the whole model selection, but that's a huge topic. So I divided into 2 sections. I'll talk about this more. I'm sorry. So why do we care? Why do we care about predictive performance? 3 things. First, we want to estimate the generalization performance. Okay, so this is a topic under generalization. Second, we want to be able to increase the performance we get. How? By tuning the hyperparameter of each model. This is what theoretically falls into model selection, okay? And lastly, we want to be able to have lots of these combos, lots of models and different configuration of these hyperparameters and find something that kind of quote unquote beats everything else. This is a topic that falls into algorithm selection. The reason the first one is highlighted is because I want it to be the focus of this talk and today's event. Hopefully, if you enjoy this talk, in the next discussion, we talk about those other 2 as well. Before I start, I have a lot of these box plots. I assume that most of you know what they represent, but I just wanted to make sure that you understand that when we represent a sample by a box plot, we get this little rectangle in the middle that, assuming that you have something that resembles a normal probability distribution, that will represent 50%, the middle 50%. And that line actually is the median. So I don't show the mean, it's the median of the the sample. And then those two whiskers that you see on the side, they stretch all the way to 95% of data. And everything outside of that will be kind of an outlier. So it will be shown with these circles. How to estimate the performance of a machine learning model? This is a very common scenario. We have a data set, we divide it into two independent training and test set. That means no sample will fall into both of these groups. They're exclusive. Sometimes it's 70% of the data that goes to the training and 30% to the test. There are different variations of this. Then we feed this training data to a model. And then what we do to evaluate this performance is that we predict the labels of the test set. And lastly, we calculate an accuracy. I mean, it could be an error, but usually it's about how many wrong predictions or right predictions did we have on these predictions of a test set. Is that really it for selecting models? This scenario is very common. It's in all tutorials, and it's been repeatedly said, and it even exists in machine learning research papers. But is this really it? I would like the whole presentation and today's event to be a suspicion over this four-step algorithm that has been repeated so many times that you kind of feel like, yeah, that's how you select models. And today it will be a lot of information, but I hope that through discussions and going back and forth, we could really understand some of these concepts. Each of these subtasks that I mentioned, those three, about why we care about this, require different treatments. This is not very obvious when you look at the problem from the beginning. You feel like, okay, so all these three, if I divide my data set, all these three will be met by this simple algorithm. It's not true. In fact, there's been cited in research so many times that estimating the absolute performance of a model probably is the most challenging task in machine learning, at least one of them. The scenario I mentioned at the beginning of this presentation is something that we call holdout validation. So let's put a name on that. And again, the focus is that these training and test set are completely independent. It's actually one of the foundation of this holdout validation. Throughout this presentation, I made up a practical example with this UCI heart disease data set. It has 303 samples and 19 features. Throughout this whole presentation, we compare a neural network, a multi-layer perceptron, and random forest. Both of these models are black boxes. And throughout these examples, I've made use of scikit-learn and MLextend Python packages. You can find the code here, and there's a link to the presentation on the right side. So you can play around. I hope I did not make bugs or anything. But yeah, if there was bugs and you found them, please let me know. Okay, so given this data set, okay, 70%, 30%, we train two models, we have a holdout data evaluation data set. This is what you get. This is the average accuracy score of these two models. I believe one of them is 83% and one is 82. If you remember when I posted about the event, I said, would you rather pick a random forest and an MLP? And sometimes these accuracies are so close. And some people, in research even, highly cited papers of AI, you have these really incremental differences in scores, and they make one of them bold. Here is like 0.224 difference between an LSTM CRF that uses the character level or the, token level. We always have these cases where models are so close to each other, and yet some machine learning model engineer or someone picks the one that is like slightly better, but fails to really analyze the situation. So let's talk a little bit about the situation, and let's try to see if we can squeeze more. Before everything else, we need to set the stage for two concepts, bias and variance. Okay, so you have two types of bias in what we do. First is an optimistic bias. When is that going to happen? This is when you train on the whole training data set. So there is no difference. Or let's say the training data set is huge compared to the test set. So what happens is that you're overconfident. In the literature, we call this an optimistic bias. So you're literally, it's as if you're just training and testing on the whole data set. But you also have a pessimistic bias. So what is this pessimistic bias? It's the opposite. It's when the test set is really substantial and the training set is not as large. So what happens in this case is that the model is not fully trained. In the literature, they call it having a low capacity. Okay? So this is two types of bias you get in this holdout situation. Okay? What about variance? There is no variance, and that is a problem. What you get is a single point that has no variance, and that is horrible for model selection because you're stuck with this point. And if they're too close, you're not really sure what risks you're taking for picking the right model. So the real question is, how confident can we be? This is a much more important question than how accurate is a model. Why? Because I could say that my model is 80% accurate than yours only 20% of times. So this is not an absolute performance situation. So we need to be confident. How do we get confident? By estimating what is called confidence intervals. So there's a missing sentence there. So confidence intervals are these ranges we get. And when we have this lower part of the interval and upper lower part of the interval, and this will give us a limit that an estimated, let's say, accuracy here will be correct, will be containing the true value of the parameter. So we want them to be really close. If they're really close to each other, that interval, then we're more and more sure that the accuracy, the mean of that interval will represent the real accuracy. If they're too wide, then we have a lot of variance. So variance usually is measured by confidence intervals. As I said before, when you have these holdout cases, there's no way to calculate these confidence intervals. And I'll show you that they actually are so confusing and so are also important in finding the best model. One way that you could easily get variance, or let's say confidence intervals, is to repeat the holdout validation k times and average the results. So this is a very empirical based way to get these confidence intervals. Why do I say that? There's not a lot of guarantee in that sense of how close these intervals are. It's just that you get something. There are other ways to get theoretical confidence intervals by assuming certain things, but we're not going to talk about that because it's a little bit complicated. Wow, this one had a transition. Okay, so let's go back to the example and run 20 times the holdout evaluation. You see two charts. I'll explain what they mean. To the left side, we have divided the test and training set to 75% training, 25% test. On the right side, we've actually divided them in half. So why this is the case? It seems that based on literature, when we repeat these events, these holdout evaluation, it is actually good if we divide the test and training and test into equal proportions and as large. And surprisingly, you can see that on the right side, these whiskers are not as long. So they actually give you smaller variance. Again, we want the smaller variance to be sure that the average of the accuracy we get is actually representing the true accuracy. So what happened now? If we just look at the right one, because that's the preferred way of doing it, you can see that now random forest is really better in providing a better average, and neural network is actually much worse. So the image that you saw at the beginning now breaks into a new image. Now you kind of realize that, that's kind of strange. But this approach has limitations. First, training and test set are no longer independent because you repeat that, and in each of these variations, you might end up with one sample once representing training, once representing testing. And usually these bounds, the variance is so high that these bounds are not very accurate. So it's a very easy approach, but it doesn't work. So how do we fix this? We fix this by a new approach, another approach, let's say, called bootstrapping. And bootstrapping, I've covered only two for the sake of the beginning introduction. There are so many different ways. And the reason I picked these two is that one is biased and one is less biased. So let's start with the leave out. Sorry, this is not leave out, that was a mistake. The original bootstrapping. So I'll tell you simply what this means. This means that we sample from the training set, but with replacement, meaning that if you pick a sample, there's a chance that you might pick it up again. And you set a size for this, for your training and test set. And it's not a very intuitive because you're like, why would I sample the same instance twice? But it actually has theoretical guarantees. So what you do is that you will average the accuracy over many of these runs. And what happens is that, so I think it will get easier. So in bootstrapping, you do what I mentioned earlier, resubstitution method. Training and test will be the same. So once you pick 50% of the data, it will be used for both training and testing. And Tishbiani, who recommended this approach, said you should do it 50 to 200 times so to get a good accuracy if you do this. So what happens when you do that? Okay, so again, you see two different cases. Once only looks at 50% of the data and once looks at 70% of data. Again, the preference is to have 50-50, but I include the other variation to see that it actually makes a difference. So on the left side, you can see that now it's the neural network that performs better. And although it has a large variance, these whiskers are long, but now it has a completely different image. So now we're using an approach that says pick the neural network basically. But there's a little bit of interesting pattern there. Do you see what happens to random forest? Random forest, when we show it 50% of data, it shows an accuracy that is like 93 and it has a large variance. But when we show it 70% of data, you can see that it's actually quite accurate. That means that in the 50% case, random forest is under its optimal capacity, meaning that it needs more data to learn something. However, as I said, the preferred approach here is to, again, divide them to 50-50 chunks. So what happens with this is that this has a bias. And what's the bias? The bias is that first, the training and test set is the same. So that's one bias. And another bias is that you might end up randomly picking up one sample way too many times and not picking some samples. So the same authors came up with this 0.63 bootstrap technique. And that is actually the chance of picking up an instance. So they adjust this by a normal weight and then do everything else. Again, if you look at the image, you can see that examples end up being in the training set multiple times. Also, in this approach, we do not perform the usual resubstitution. We do not test and predict on test and train. We actually separate them like a holdout method. This is actually the most, among the methods that I talked about, is the best method because it doesn't have, it uses both the independence, but also the bootstrap. What happens now? Now it's neural network that performs better. However, you can see that it has a very large variance. So it is really confusing, right? Even in the simple case of a UCI data set, now we end up in these cases where in all of them, one method is better. And sometimes some methods have large variance and sometimes they don't. but still, the question is, what do we pick? I showed you 4 cases. You can see it here, the average accuracy of each model. And then you can see the confidence interval. Again, the way you read it is that 95% of time, for example, for repeated holdout, the accuracy will be in 77% and 86%. Okay? So when you look at this, it's not that easy to pick up a model using cross-validation. And this is about really today. This is what we're going to talk about today. If we go by the 0632 bootstrap, then it's the neural network that wins. If we do a repeated holdout with 20 times, then it's the random forest. I will just leave the discussion with this quote. It's from Bengio and Granvalet. They actually studied this this bias of the cross-validation, and they said that there is no universal unbiased estimator of the variance of cross-validation. And that to me is very strange, because all these talks, when we have papers in machine learning, when we do it in companies, when we do the model selection, it comes off as such an easy task that we just report an average accuracy on the holdout data set. However, just looking at these examples, and probably many more that you know and I don't know, it doesn't really come intuitive. So this is where the presentation ends. We will divide you in groups. I'm really interested. I picked a series of kind of questions. You can do them too. But I picked up a series of questions about what to discuss today. And first and foremost, how did you evaluate the generalization of models before the event? And which one of the methods included in the presentation or outside sounds more rigorous to you? You could discuss about the case. There is a link to the presentation. Try to simplify the concepts. So if you don't understand the method, try to understand it or discard it if it doesn't make sense. And make sure to be inclusive in discussions. We all come from different backgrounds, and some are more talkative and some are less talkative. So try to enable everybody. And if someone doesn't know or lacks a certain information, please make sure that you explain and get that person on track with the discussions. Great. I'll stop sharing and okay. So now you can join different breakout rooms, and you can take a 5-minute break. The discussions will be around 40 minutes.